Hello students. In this short video, I'm going to discuss the difference between a state vector and a wave function. So we know in the quantum mechanics, the state of a quantum system is either defined by a state vector or by a wave function. So wave function can be in position space, or it can be in momentum space, or it can be in spin space. So what is the difference between these two representation? So state vector is basically a coordinate free or basis free representation. So the state vectors are the element of a Hilbert space. What is Hilbert space? Hilbert space is a complex vector space equipped with an inner product. So now these state vector, they have full information or complete information about the system. Now these wave vector can be projected on different coordinate spaces. For example, if I take the projection of psi on x-axis, this will give me the wave function in position space or position space. Similarly, if I take the projection of psi on momentum space, this will give me the psi p. Similarly, I can project this psi onto a spin space. So let me discuss this notation with an example. For example, say I am taking a example of two-dimensional vector space, real vector space, which is called Euclidean space. So in Euclidean space, I write a vector A as say C1 x cap plus C2 say y cap. So for example, I have a two-dimensional real vector space, which is an example of Hilbert space. Hilbert space is a bigger set, so which contain complex vectors, wave functions. While here, in a Euclidean or two-dimensional real vector space, you have only real vectors. Here you have only real vectors. So any vector, say A. So any vector A has can be only can have only components either in the x direction or y direction. So this vector is basically combination of two states. One is the x state and one is the y cap state. In general language, we call this a unit vector in the x direction. This is a unit vector in the y direction. Now in drag cat notation, the same vector we write as a cat. So I can write just C1 and I can say this is my X, and I can say this is my C2 and this is my Y. Say Y. Now these X unit vectors, these are the state vectors of two-dimensional Euclidean space, that is XY coordinate system. Now, suppose if I want to get a coordinate of or projection of this operator on x direction. So what I'll do generally, if I have a, so I'll multiply this by x cap. So when I multiply by this by x cap, I get C1. Similarly, if I want the y component of this vector, I multiply by unit vector and I get the C2. So in a matrix form, I can represent, say, this A or a state vector by two components. Two components are C1, C2, and this is in the basis of x cap and y cap. So x cap and y cap are the basically states. So in two-dimensional space, you have only two states, and any other state can be combination of these two states. Now, so this is the example of just two-dimensional space. For example, we have a three-dimensional space. So we will having a C1x, C2y, we'll have a C3z also. Similarly, these are finite dimensional spaces. Now, Hilbert space can be also a infinite dimensional space. So when you use the infinite dimensional Hilbert space, then your state vectors becomes functions. For example, these are the constant vectors. Now, if I same vector, if I represent say a by say if I represent this y as a x square, say x cap, or y square, y cap. Now, if I say find the x coordinate of x component of this vector, so what will the x coordinate of this vector? So this will be your x square. Now, this is these components are continuous. So, for example, if I want to represent, now this will be what? This will be the x component of this vector, and I can say this is my ax, and ax is equal to x square. Now ax is the function. Function means a function is equivalent to infinite dimensional vector. So this ax is basically what? This ax is the basically a state vector with infinite components, where I am taking the projection of A, on x1, say projection of A on x1, then I'm taking the projection of A on x2, then I'm taking the projection of A on x3, and so on. And these are the continuous up to infinite components. These are infinite components. So a wave function is basically a infinite dimensional vector. And so now if you say ax, now this can be equivalent to x square. So it at each x position, okay, at x1, the projection of A on x1 will be x1 square, projection of A onto x2 position will be x2 square, projection of A on x3 will be x3 square. So because these are continuous, so we can represent them by a function. So the same vector, generally in electromagnetic theory, we say it is the vector field. Vector field, because each position you have a physical quantity is changing with the position. So this is the basic difference between a wave function and state vector. So when you have a state vector and you project on x, you get the wave function. Similarly, if when you project psi on a momentum, you get the momentum space wave function. So these wave functions have a infinite component, or they are continuous. So we represent them by a function. So more detail and examples of these two things I will be discussing in my next video. So hope you like this video. Thank you very much.